Welcome to CBSE.
Have you ever stopped to think that the entire world, everything around us, is basically telling a story? A story that's being written and rewritten every single second? Well, that story is written in the language of chemistry. And today, we're going to learn how to read it.
They're all telling the exact same kind of story. It's a story of transformation. It's a story of a chemical reaction. And by the time we're done here, you'll see it too.
So here's our game plan. First, we're going to become chemical detectives, learning how to spot these changes out in the wild. Then, we'll learn the secret language chemists use to write them down. After that, we tackle a huge universal law. In the Great Balancing Act, meet the main characters in the world of reactions, and finally, see how all of this completely rewrites the world you see every day.
So, how do we actually spot one of these invisible transformations? I mean, it's not like they wave a little flag and announce themselves, or do they? Well, it turns out chemical reactions leave behind some really obvious clues. We just have to know what to look for.
Just think about it. That sharp, tangy smell of milk that's been out a bit too long. The reddish-brown flakes that appear on an old iron pan. The incredible way grapes turn into wine. These aren't just random things happening. These are all stories of fundamental change, where a substance becomes something completely new.
And that right there is the key. You see, a physical change is kind of like changing your clothes. You're still you. Ice is still water. It's just in a different state. But a chemical change? Oh, that is a total transformation. It's the caterpillar becoming a butterfly. The original stuff is literally gone and something brand new is in its place.
So, what are these clues we're looking for? Here's your detective's checklist. Do you see bubbles appearing out of nowhere? Has something changed color unexpectedly? Do you feel a sudden burst of heat or maybe a surprising chill? If you see any of these things, you're not just observing, you're witnessing chemistry in action.
Okay, so we're officially chemical detectives now. We can spot a reaction, but how we, talk about it? We can't write a whole paragraph every single time something fizzes. We need a shortcut, a secret code. And that's exactly what we're going to learn.
We can start by getting rid of the long sentences and using something way cleaner, a word equation. It's simple, it's tidy, and as you can see, it gets right to the point. What went in and what came out. Done.
All right, quick vocabulary check. The stuff on the left of the arrow are ingredients. We call those the reactants. And the new stuff that gets made on the right side, those are the products. Reactants react to produce products. See, it's pretty straightforward. But why even write out the words? We can make it even shorter with a skeletal equation, using the symbols from the periodic table. Mg for magnesium, O2 for oxygen. It's the ultimate shorthand. But there's a problem here, a big one. This equation, as it's written, it's breaking a fundamental law of the universe.
And that brings us to the Great Balancing Act. Now, this isn't just about making our equations look neat and tidy. Oh no, this is about cosmic justice. It's about upholding one of the most important rules in all of science.
This is the big one, the law of conservation of mass. It basically means you can't just create atoms out of thin air, and you can't make them disappear either. A chemical reaction is like a game of cosmic Legos. You can take your pieces apart and build something new, but you have to end up with the same number of pieces you started with. Always.
Okay, let's put this to the test. Here we have a reaction. Iron reacting with steam, which is basically a type of rust. So, is this equation following the law? Let's investigate.
And, whoa, the numbers don't lie. Look at this table. We start with one iron atom on the left, but we end up with 3 on the right. We start with one oxygen atom and magically get 4. This is a problem. We're creating matter out of nothing, and that's a huge violation of that universal law. We've got to fix this.
So, how do we solve this puzzle? Let's start with the most complicated part, that Fe3O4. It's got 4 oxygen atoms, so let's put a big 4 in front of the H2O on the left. Okay, that gives us 4 oxygens, but it also gives us 4 times 2, so 8 hydrogens. No problem. We just put a 4 in front of the H2 on the right. Now our hydrogens match. And last, we see 3 irons on the right, so we just pop a 3 in front of the Fe on the left. Now let's do a final count.
And look at that. Balance is restored. 3 irons on both sides, 8 hydrogens on both sides, and 4 oxygens on both sides. The universe makes sense again. And those little letters in parentheses, the S and G, they're just telling us the physical state of everything. S for solid iron and G for gaseous steam.
So we've learned the grammar of chemistry. Now it's time to explore the different genres. Just like with movies or books, chemical reactions have their own common plots, their own classic stories. Let's meet a couple of the main characters.
First up, we have the combination reaction. This one is super easy to remember. It's basically the romantic comedy of the chemistry world. You have two or more different things that come together to form one single new thing. Two reactants go in, one product comes out.
A classic example is when quicklime meets water. And let me tell you, when they get together, sparks fly. This reaction gives off a ton of heat. That's one of our telltale signs, right? A change in temperature. Because it exits heat, we call this an exothermic reaction.
And on the flip side, we have the decomposition reaction. If combination was the rom-com, this is the dramatic breakup story. You start with one complex thing, and it breaks apart into two or more simpler things. One becomes many. But this kind of breakup needs a little push. It needs energy.
And that energy push can come in a few different forms. You can use heat, which is called thermal decomposition. You can use light, that's called photolysis, and it's why silver chloride turns gray in the sun. Or you can even use electricity to zap things apart, which we call electrolysis.
Okay, so we've learned the language, we've learned the laws, and we've learned some of the main stories of chemistry. But what does it all really mean? Why does this matter to you?
It means everything. That rust on the nail is a chemical story unfolding in slow motion. The bread rising in your oven is another one. Heck, every single breath you take is a high-speed chemical reaction keeping you alive. The world is a giant library of these chemical stories, and you've just been given the key to read them all.
You now have the key to see the hidden script of reality, from what's happening in your kitchen to the farthest reaches of the cosmos. It's a secret world that's been right there in front of you this whole time. So now, the only question left is, what chemical story are you going to uncover next?
Thank you for watching with us. See you next time.